Hello, my name's Brent Young. I'm from the University of Auckland, and I'm going to talk to you now about the engineering of smart digital twins for decarbonising process heat. This is a collaborative study between my own university, that of the University of Auckland in New Zealand, and the University of Waikato, another university in New Zealand. So let me share my screen, and we will get right onto it. So, yeah, here's my collaborators from the AHU, my colleague from the University of Auckland, and Dr. Patros Wormsley and student Elsa from the University of Waikato. So I'm going to be talking to you today about digital twins and how to engineer them for decarbonising. This is actually part of a larger study termed AHU Aura, which is the development of a digital twin platform to help New Zealand industry decarbonise. This is a 7-year project of where we're funding multiple research students working with 3 universities and industry to help with providing tools to re-engineer the way New Zealand converts, provides and stores energy for process heat. The idea, the overall aim, trying to make a more sustainable New Zealand and more sustainable New Zealand industry. New Zealand, like a lot of the world, has been pushing for decarbonisation recently. So there's been several key documents and key things happening in our decarbonisation space down under. There's been changes to our Local Resource Management Act and a ban of the use of coal-fired borders. At the same time, there's been a Climate Change Commission, which has provided some aggressive advice about getting to a low emissions future for New Zealand, or Aotearoa, as it is. The country is also known in Māori, our local Indigenous population's language. So the government investment is occurring in decarbonising, putting in helping industry put in, for example, biomass boilers up and down the breadth of our small country. So how do we decarbonise industrial processing? Well, it's about the process itself. It's about the industrial site. Also, how does that connect to the community? So what we and others term the factory edge. This is particularly relevant to the regions in our country, and then of course nationally when we collect this up. So we need to be looking at right across this space. So our first aim is in the process area is to reduce energy demand through better control and perhaps development of new assets and new technology. And our secondary aim, although that implies a hierarchy, it's not necessarily secondary. In parallel, we want to improve energy conversion and through higher efficiency use of utilities and high efficiency, high temperature heat pumps. And then at the factory edge and regional area, we want to be looking at sourcing renewable energy, electricity, biomass, and integrating with the community. Now, here's a plot that shows you the future energy demand or electricity demand predicted for the next 30 years or so. New Zealand's quite, well, it's not sort of shown here. This is the electricity demand. New Zealand's quite lucky that most of its electricity demand is not from fossil fuel sources. It's from sustainable sources such as hydro, geothermal, and wind, but not solely. And some of this increase has to, the demand is coming from, it's got to be supplied. So you can see here that we've actually got a considerable increase, driven a lot by not just base growth, but by things like vehicle electrification. So here, as I was saying before, the install capacity and generation capacity in New Zealand is, a lot of it is, in fact, decarbonised already, with significant hydro and wind and geothermal and solar coming on stream. But so we need to be investing in install capacity to help meet the demand that we just mentioned before. Now, in turn, that's sort of setting the general scene, if you like, of the background for this. In terms of what are digital twins, we've looked at this in a detailed way for the process industries, but in general, just to remind you, it's a term that's been used for the last 10 years or so and refers to a digital model that is, in some ways, looks like, is connected to, and behaves like a real plant. And so there's various levels of digital twin, coming from that basic digital model through to what some people have termed digital shadows and full-on digital twins. So we felt that actually when looking at the literature for digital twins and for digital twins in power and in decarbonisation, that this is the term gets, shall I say, bandied about, and is somewhat inexact. So we wanted to really understand that from a literature point of view. So there's a bit of a word cloud here shown on the right, and you can see there's a lot of different words of very similar emphasis that are used in literature when searching on digital twin and process heat. So this sort of shows you that perhaps the field is not that mature. We also looked, as you can, on the right at the literature as to what the drivers might be for applying digital twins generally in processing. And what was interesting is that, in fact, and encouraging, dare I say, is that the primary drivers, if you look at the pie chart here, is around things like energy efficiency, decarbonisation. They are actually pretty high if you actually sum them up. You also, of course, will see the economic imperative as well through, quality, throughput, and profit. Naturally, make a high showing as well, as of course does safety and risk. So we're actually in quite good shape, and it's encouraging to see others are thinking about this along the same lines. Secondary drivers, of course, are actually also you start to see there that that the flip side of that, that it's one or the other, that energy efficiency and decarbonisation are important, either as a primary or secondary driver for digital twins. So as a result of the literature survey that we did, we feel that the best way of characterizing a digital twin is explicitly this. It is a digital representation model that looks like, behaves like, and connects to a physical system. And what does that mean? Well, if you actually look into sort of fidelity, say of looks like, behaves like, and connects to, there can actually be different levels of complexity. So we've in our work have defined 3 basic levels, and can see 3 basic levels of each. In terms of a looks like, you might go from a 1D type representation, such as a process flow diagram, to a full-blown 3D CAD model, for example. That's in terms of what does your digital twin look like compared to the actual process itself, the process twin. How does it behave? It could be, in terms of fidelity or complexity, it could just be a mass balance model. So single states, or quite static. Or you could look at many different operating states, or in fact look at transients and dynamic things, such as process control. And then how this digital twin connects to the physical twin is also a key part of the complexity defining the type of digital twin you have. It could be that it's indirect, and that it's perhaps it's a digital model that is being used for advice, providing decision-making advice, but it does not have an automatic loop. Or it could be completely connected, or so you've got automatic control invoking the digital twin. So at the highest level of complexity. So what's interesting is if you start to map out some of these types of fidelity. For example, here we've done this for the looks like behavior and the behavioral like fidelity. Now, obviously, when you've got the most complex, you've got the most computational intensity, and that's sort of shown by the color in the diagram here. But also what this kind of indicates is there may actually be some gap in the sort of 2D looks like fidelity area in terms of application of digital twins. And you can see here, for example, like a single steady state block flow diagram type model is the lowest level of computational intensity, and we've seen quite a bit of them. The transient CFD, which is used for dynamics 3D, it's very high fidelity from looks like it behaves like, although it may not. What we haven't shown here is that third dimension, the connects line, may be lower in that ranking scale. Another aspect that we uncovered in our work is that the idea of a physical twin that must adapt with its physical twin. Things do not stay the same. We need to consider, things, consider change in our models. So, failing, denaturing of catalysts, but also changing topology of the physical twin, etc. So our digital twin needs to adapt to that, and this could be in a programmed adaptation type way, or it could be in a far more autonomous adaptation. So again, this is a category that, an area that further work really needs to be carried out in. So what we've developed is that we're, for our work in decarbonisation, is that we need to be looking at developing tools that are, digital managers, or digital twins, if you like, that have that the high level of those 3 attributes, but also adapt with time, have some sort of adaptive attribute. So you can use these digital twins for what-if or optimization type studies that are integrated to not just the plant, but also to the site edge, the industrial site, the government, the ownership of the business, and so on, so that we can truly add benefit and with these digital twin models. In conclusion, what we've found is that there's a number of research directions that we need to take in looking at applying digital twins towards decarbonisation. What we've found, in addition to what we've already mentioned before, is that there's a gap when it comes to service applications. Also, applications to multiple different scales, and this could also be another characterization category that we could consider, and application to the full life cycle. We've already mentioned the adaptive digital twin technology being a key future need for this area of decarbonisation, but also the software requirements themselves need significant work. So work into the security of the platform, on the sovereignty of the data and the frameworks for that. What are the requirements for software engineering of the tools that we need to develop here, and generally, a general approach for engineering of artificial intelligence-driven digital twins. It is fair to say that most of the digital twins to date that have been successful have been some sort of fundamental or hybrid model, but AI-driven digital twins, there is a lot of engineering that needs to be done to make these robust and adaptive to be useful in this particular space. So what I've done in this brief recording is present to you the results of some initial research on the engineering of smart digital twins for decarbonising of process heat, particularly from a New Zealand perspective. We'd like to acknowledge the support of AHU Aura, which is a platform funded by the New Zealand Ministry of Business, Innovation and Employment. And in addition to my co-authors, I'd like to thank the wider team of researchers at the 3 universities in New Zealand that are undertaking this work. Thank you very much.